point now, much better, much better. All right, so the issue here in machine learning is that the Jeffersons of the world say you just throw data and parameters at it and it works. And I had a long talk with John a couple of days ago about him being upset that we don't understand anything. And so this is just papers I looked at saying what we understand. So you have a typical neural net, you have some training data, and in this case, the number of parameters, the number of weights is going to be much bigger, polynomially bigger than the amount of training data, which people say, hey, Park, people say this might not be interesting because if you have these many parameters, you can just do table lookup, right? In depth2, you can say if the input's this, do this. And with that kind of overfitting, then you don't generalize well. And so the two issues I've been thinking about is how quickly does this, can you find a solution, and what do we know about overfitting, about generalizing? So at the end of the talk, there's not much we know there, but I'll tell you what I know. All right. So here's the question: is how fast does gradient descent find such a solution, and how quickly does it find it, and does it get stuck in a local optimum? So my understanding always was that we just didn't know anything about this, and we just hoped, right? And so what the main paper proves is that it finds perfect, a machine that gives perfectly the answers in time polynomial in the number of training data. So note that this isn't polynomial in the number of bits to the problem. It's polynomial in the training data, which is going to be much bigger. And 7 looks like a big number. And the paper says we can shorten it, because lower 7, they erred in the side of readability instead of smaller number, and the paper wasn't very readable. So all right, and what I find also interesting is for those people who want to understand the neural net, the neural net that this comes up with is pretty much random weights plus a small undetectable change. So it won't look something you can understand. And what that says is, at least in this huge space, the networks look random, and so they're not explainable. Optimal means it gets the perfect answer on your training data. And I only say epsilon because we're doing real numbers, and so all right, so and within this really large space, the number of these optimal solutions is, I mean, a random one, you know, is good. All right, so what's our model? The paper says it covers lots of models, but it focuses on one, and the one it focuses on is real numbers. So we're doing regression on real numbers, and the error is kind of what you would your standard sum of square error, which is you sum over all the training data, you sum over all the outputs, if you have more than one output, of the difference between the answer the machine gives and the answer that's that comes with the input. Right. Sorry, what? This is the output of the machine, and this is the output that the supervisor gives, right? And you take the difference and you square it, right? And you sum up over everything you sum up. right? Yeah, well, you want to do all training data. And now, in this case, there are many. R is, see here, R is 4, right? There just happens to be one output. Yeah, because these are, this is the Y vector is because they're 4, and I'm taking the second one. All right, and then we're going to do this activation function, the rectilinear one, which I find is a pretty cool looking one. And the reason they do this one is because previous papers had done other ones, and this was one of the new improvements, and it's a little harder. And then, as I say, at the end of this, we'll talk about all the models it covers, but these are the models we're going to deal with. Oh, well, the classic one is the sigmoid. Yeah, but it claims to do it for anything that, and you give reasonable properties. All right. All right, so now let me just give a disclaimer. The paper is 53 pages of quite hard math, and which I didn't always read. And it says in its disclaimer that if you throw things under the bus, then the math is much easier. And so I think what I did was I threw things under the bus, and the math was pretty easy. And I'm not even absolutely sure where I was being cheating, but often I'm sure I am, right? Because they're, yeah. Excellent. Because what I do is here is surprisingly easy. And so assume that, so some obvious things I'll say we're not going to deal with that. And I'm sure there's things I just cheated. All right, so this is just standard gradient descent. You know, we have our spaces for weights, we have the height of the error, you have given weights, you find the change the weights in the direction to decrease the error as fast as possible. And what's when we were grad students, what did we worry was going to happen? We worried that there were lots of local minimum, and one of the minimum is slightly better than the others, and you take exponential time to search the whole space to find it, right? What's the best case scenario? It's kind of there are lots of local minimum, but they're all optimal, right? So you just can't, in some ways, can't go wrong. So what you do is you start in a random place and you travel a very short amount of time, and you find one, right? So that's what we're looking at here. And so that's this paper claiming it happens. All right, and it requires this over-parameterization. All right, so what do? We start with random weights. And then we only travel, it's going to be a short algorithm, right? We're going to find something very fast. And within that fast amount of time, we don't travel very far, right? We have to prove that we stay within some little ball, right? And here, so here's the change to the random weights, right? Here's the random weights, here's the small change. This change is small, we're within that ball, right? And now within that ball, we don't know where the gradient descent is going to take us, right? So we assume that an adversary puts us in the worst case position in that ball, right? But it also gets upset when you bump the screen. There you go. It also has to prove that we stay within the ball, right? So now, what about weights? Well, we all understand random numbers because you have lots of them. So things happen with high probability the way you expect them to. And then if you shift just by a little bit, you can prove that the behaviors that we care about don't change, right? Within random weights, we get the behavior we want. And if you don't move by very much, then you still get the behavior you want, right? Does that make sense? No? No, I love Aaron. I mean, for many reasons, but you have the best place for, I don't understand what we're talking about. Oh, I haven't said that. What we expect is that gradient descent works well. Right, so it's just that there's some properties that are true for random weights, and we'll give it to you. They're not hard to prove. And then we'll wave our hands and say, if you change your weight by a little bit, those properties will go away. Right? And as long as you're in the ball, you're good. And then we prove that the gradient descent works so well that we find the solution before they can fall. Yeah, in fact, I had a picture from the top, maybe of the next that showed that, and it just, but it was a pretty fine picture. It showed flat manifolds. So yeah, within the ball, things are relatively well behaved. No, it will have bad air. But it's good in the sense that gradient descent will work well. And you have to the right space. Otherwise, there's a lot of that you start going, you won't go anywhere. So make sure the starting point is within space. Yeah. You can use the within. Yeah, so what's really fine-tuned is what the distribution is on the waves. They have to be this particular, but within that distribution with exponentially. For example, you give you lots of yeah. So these are it's a distribution on the waves. Yeah. For which, with high probability, a random one will have a rate. So generally all the 0, 0, 0, 0. Lots of yeah, but that happens with very low probability. So give you all right, well, why don't we see what hold that thought and let's see what we do and see if you have disagreement. All right. The behavior is gradient descent works well, right? And we'll define that in the next 3 slides, I think. Yeah, gradient descent gets you the answer in fast. That's the joy. It gives you, of course, it always gives you a local answer, but it proves that it works well enough that that local answer is perfect. It's perfect. Yeah, so you can prove the theorem that this basin is better than that basin. I mean, it's such a big space. You're not going to prove that. But if you can prove that this basin is perfect, well, I'd say if they're real numbers and you grow exponentially close to it, then you get the epsilon. But the minimum itself is the actual. It's perfect. And yeah, which is a serious problem that you get stuck in plateaus. So you will not solve them. No, it's I thought it was kind of maybe 27. Oh yeah, that's correct. It's number of training data to the 27. Right? Yeah, so really you have a lot of parameters, right? This says nothing about the number of inputs to your problem. It's you're given this training data and you want to learn this training data, right? So yeah, exactly. 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 So what properties do we want? We want that, and here's our weights and our error function. We want to start in some random weights, and every time you step, you want the error to decrease by a constant factor, right? So that in exponential time, in log of the error time, you get within epsilon of what you're looking for, right? So let's see what we need to do to prove that, right? When you do gradient descent, you take your current weights, you look at the current error, you take the derivative, and you get the derivative of your error with respect to each of your weights, and then you have some step size, and you take a step in that direction, right? And so what we're gonna get rid of this, and this is what we're gonna be looking at, is that the amount a particular weight changes is by the step size times the derivative of the error with respect to that weight, right? So now you want to calculate what the new error is, right? What is the error when you have weight plus the change in weight? And our first approximation, of course, is going to be the linear one, right? So it's the weight the error that we had with the old weight plus the slope times how far you moved, right? And then, well, you can see it from the picture that that's not good enough. So you're gonna, when you do the Taylor expansion, you're gonna have some change squared, terms. And even worse, this doesn't happen when you have the sigmoid function, right? But when you have this function, this isn't differentiable. So there's some really quite ugly terms that arise because of that. And the key is that all of that goes away if your step size is small enough, right? Which makes sense. And that is why we set the step size to be small, right? So 1 over polynomial in the training data, and that is why the time is as big as it is, right? It's not because of the log of the error. That's not a problem. It's the step size is really small, and so that's why you need a bunch of time. Yeah. You're saying sigmoid is worse?
Yeah, it's not work first, but say here.
Yeah,
Bigger
yeah. Yeah, so here they say that their proofs are better. They didn't give what this number would be, but they said when you have this, you don't have these terms, and the 7 goes down to something smaller.
Just keep those counter.
Yeah, yeah. It only have one sentence. It did say in one sentence that some of the ugliness comes from this. All these ugly terms, this term is just what you're saying. Right? And this term is kind of ugly because they're trying to deal with this form. Right? Yeah, yeah. All right, so we're going to ignore that's one big thing thrown under the bus, right? There's 10 pages right there, right? All right, so now we're just going to play with this linear thing, and so our change in weights, right, is the step size times the derivative, so we plug that in, right? And then here we just rearrange. You get a square there, which is kind of fun. And then we have to sum up over all of the weights because we do this for all weights. And then I must admit, yesterday, just before going to bed, I panicked because I didn't really know where to put this sum. I was putting it in the wrong place. And so I just sort of guess where it went. I'm pretty sure it goes within the square. But the problem is that these guys can cancel. Right here, this is summing over all the training data, and it's one change for one training data can cancel out another change for another training data, and so that becomes the problem. But when you sum over the different weights, changing one weight won't cancel changing another weight. So I might have some things wrong in here, but all those details are going to put under the bus anyway, you'll see. So which? Yeah. Here, I was focused on change. And then I stuck these in and said, try to make it easier. One change. Now, oops. So this isn't really equal. Here we're talking about the whole change. Right? Everything. Yeah. Yeah. Yeah, everything is. Oh, there's no factors here. This is some over which, yes, so this bit up here only changing one way. And we're asking what the one error, how the one error changes, right? And then, as noted, it kind of switch to we need to change, we have to do that change for each of our weights, and we have to do it for each of our training units. Right? And then we need to prove that this change is proportional to the error. Right? That's the whole point. If you want the error to decrease proportional to the error. Right? So we need that to make sure that that proves the claim, right? And we also need to stay within the ball. So you need to make that the change isn't too big, right? Because if gradient descent work too well, it moves the weights too much. Well, this is kind of a red herring here, because it's the weights that we want to prove don't change too far, but their theorem says this, so I stuck it in there. Anyway, you gotta make sure you stay within the ball. And so so what we're gonna do is we're gonna look at 1x and prove what happens for 1x. And then dealing with the many x's is going to be thrown under the bus. All right. So we're going to look at maybe one training data, and I'm going to show that the change in we're going to take one training data. We're going to do gradient descent for the one training data. Okay. We're going to show that the error is by some multiplicative amount.
That's how you
Yeah, so they have batch sizes. So you could calculate the error with respect to all your data and take the derivative with respect to all your data, right? Or you could do it with respect to, because it's all linear, and you do it with respect to each training data batch size 1, right? So again, we're kind of doing batch size 1 and seeing how if you have one training data, how well does it do, right? And then we need to combine them for all the training data. And this bound is easy because you can just multiply by the number of training data, right? But the other bound is not easy because you want to make sure that the changes, right? And so to do that, let's go back to what it is we're trying to do, right? We have some input X with its required output, right? And what would happen if two of the training data effectively have the same X, right? But have different answers? Then there's no way you can get the right answer, right? And so they bring in another parameter, which is the minimum distance between any training data, right? Because if they're too close, then that's a problem, right? And then this is a big throw under the bus. The delta comes into the result there. Are people following this?
So before you had the minimum distance requirement, that statement was not true.
Sorry, which second?
So before we introduced that data point should be far enough,
Yeah.
you still had that lemma that it reduces at least by a constant factor. Why would that go?
Yeah, so if you just have one X, we'll bound how much the error changes for one X. Now, if you're doing an upper bound, then the most it can change is one X times right? But in the opposite direction, I get my one X, it does one. Now all these other X's, in the worst case, they cancel me, right? So the total change is going to decrease, but it can't decrease by too much. So it can't have a if you have the same Y answer, right? But here, remember what we're trying to do. We're trying to
this. And now you're saying that you want separate it off? Like there's something that
Well, the not being close to the bend in the rectifier has to do with what values you have, and are they random, they'll be further enough away. If your weights are random, then you won't be right at the middle. So I think that's a separate issue. This is an issue of, if I look at one training data, it tells me to go in this direction.
Yeah.
If I look at another training data, it tells me to go in this direction, right? Yeah.
That could be weaker assumption.
It's a weaker than,
Them saying that the target function is.
yeah, it doesn't say anything, it just says you can't have two endpoint x's that are too close together. Well, it says nothing about the output. The output, like, what am I-
Y and Y, sorry, YD and YD.
yeah, it says nothing how, if you move over to this picture, yeah, I mean, it's certainly related. These can't be close, but we say nothing about how far these can be as far apart. Once these x's are not too close, the y's can be as big as you want.
Yeah, yes.
Right. Now, it probably, in the paper, we can replace it with your assumption that the slope's not too big. Because as Bart says, you have the exact same x with the exact same y. I'm going to go with less than the price. Yeah. Yeah. All right. So we're not going to deal with that, right? That's another nightmare section. All right. All right, and we're doing regression, so the y's are real numbers, right? But the paper works for labels too. All right. All right. So what we're going to focus on is one training data, right? And looking at the derivative of this change, how does it compare to the error? All right, because this isn't very hard. All right, and I'm only doing the easy parts. Oh, yeah, so sometimes I'm a little slack about what do I mean by an O. It can have a one over n in it. Right, so it could be the error, n is the number of parameters. So if there was a 1 over n, then you just have to do it more. In fact, I think there are if we go back. To where we to here, right? I mean, our step size is already the training data over, right? So when I said big O, I think I just hide it. And that's why the time used to be this, right? And then you talked about an extra, that was an extra n we multiplied, right? Which is maybe getting us from the -5 to 5 to the 7. Right, that's probably that one extra guy in it. Right, does that make sense?
Yeah, actually changing the change is really small.
The set size? Yeah, the set size is really, I mean, we have lots of training data, and the set size is really small.
But also the change is really, really small.
Yeah. Yeah, well, because our step size is pretty small. Well, if it's always, the current value divided by n, it's a change, then you do it n times, and you've gone down by a factor of e. Right? 1 minus 1 over n. Sorry, what?
Go back to the next.
Yeah. Yeah.
Really, I don't think I mean, if I just go change it slightly on the change of the function, then it will
Yeah, well,
but on this photo different slides,
which slide?
the what
Step size is here. Yeah.
This is not security.
That's absolutely not a big deal. Function.
Yes.
Yeah, that's what we're going to do now,
Oh,
right? All right, so yes, I mean, all the other stuff, you know, I can, where are we? Here, this is what we're going to do now. We're going to consider one training data, and this is how much the air changes by, and we're going to show that it's proportional to the current value of the air. This is what we're going to prove. We're going to prove it for two reasons. It was back at the handle, and it amazed me. Right? And I'm glad it amazes you too, because, all right? All right, so let's try it. We got our machine here. We start with random weights, and each weight is normal with this. You know, the expected value is 0, so you're plus or minus. You got a certain variance, and much of the math we're doing is simply surely there's some variance. We don't want things to grow, and so you set the weight size so that they don't grow if they don't want. And so, they first number of parameters is this times this, and just to make it talk about fewer parameters, I'm kind of throwing under the bus that the depth is a constant, and so this is n is the width, and I'm ignoring the depth. So, and you know, you can throw in depth parameters anytime you want to. All right. So this first layer, of course, is when you get n, and then it goes up to your really big n. Right? And then you have a certain number of layers. So when we take our training data, and we're going to normalize it so its Euclidean length is 1. Right? And why were the weights set to be this? Is because we want, so at each layer we have a vector of those values, right? And the length of each of these vectors will stay pretty much at 1. But you don't want things blowing up.
I just want to for the
Which values? Yeah, so I'm going to prove to you that this is the case.
Okay.
right? We set, I mean, so we set the weight small. We need the small weights, right? They're less than 1. So we set the weights so that the size of the vector stays at about 1. All right. And so just because it kept muddling me, the width. Oh, right, but we stay within our little ball. So right now we're just taking our random weights, and then we'll again throw under the bus that if you don't change by very much, then we're fine. No, you prove that in the time it takes to get the answer, the weights don't change enough to make a difference. Yeah, exactly. You have to prove there's a lot here, right? Within the time, you're given a certain amount of time. Well, maybe this paper will help you knowing what things you need to do to get it to work. All right. All right. So here we want each vector along the way to have length 1, and here's just I'm gonna more or less do this proof 3 times, because that amused me. All right. And here's the really crazy one. All right. Exactly. So suppose we have these values whose length, whose the vectors of length 1, and we're computing these values. They're blue because it's before you put it into the rectifier, right? So you get, this is coming out of the rectifier. Blue is this sum, linear sum of the inputs, and then we'll put it through the rectifier, right? So what is this blue value? It's simply the sum of this value times the weight, right? And then, well, the weights are plus or minus 1 over square root of m, right? Because of the way we chose them. And the y value, right? Because the sum is 1, each y value is plus minus 1 over square root of m. And because we want this to stay constant, is the output needs to be about that, right? And the problem is if you add up m, you get the wrong number, right? So what's happening is that these pluses and minuses have to cancel out, and it becomes like a random walk, right? You flip a coin, one of the same terms to be positive and negative, and so the difference between the positive and negative would be the random walk would be square root of m, right? And so then the math works out. Does that make sense? All right. This is my cheat proof. This is my cheat proof. No one's going to claim this as a proof. I have 2 more expensive ones. All right. So it's because. Yep. This here? This? We're trying to prove that if the input length is 1, then all of these are 1. Length 1.
WI is the weight of.
Yeah, the WIs are the weights. The the y's, the vector y's are the values along here. And we want this square plus this square plus this square to add up to 1. Right? So if the squares add up to 1, then I'm just saying each one is approximately 1 over square root of n.
W is the base on the green arrows of
These green arrows. So weight ij comes from here to the j point here. Yes. Yeah. We're just right now, we're just doing initial. We just started with random weights, and we're asking, what does this thing look like?
so there are n square many company.
Yes.
What is y line?
Yi is the ith one here. And so look at the sum here. J is Zj is the jth one here. And what is this jth one here? It's the sum over the i's of the value of this ith value times the value of this weight. Yeah, so here, this is the output of this neuron. Yeah. The purple values are the output of the previous layer. And the blue values are the output of the linear sum before we put it into the rectifier. Right? Right. So this is the linear sum of the output to the previous neurons. Right? Everybody go to this? Yeah, we're doing it by induction, assuming that this layer is length about 1. Right? And then yeah, all right. So the reason I didn't like the expensive proof is because this helped me learn about variance more, because it slides all the random walks under the rug. All right, so we know that the weight's normal. So if you multiply it by a constant, then the variance goes up by that constant squared, right? And now here's the part that throws it under the random walk. If a variable is the sum of variables, then its variance is sum, right? Which is where the square root of the length of the walk comes from, right? And I must think about this for a while. Prove that this is true about your variances, and of course it requires that they're independent, right? But well, in this case, they're thinking of the y's as constant, and the differential is independent. Right? Let's just work on beginning. We'll throw the rest under the bus. All right. It's a big bounce. It's a 50-something page paper. All right. Right.
Yeah.
Right. Exactly. All right. So that's, we get our result, right? Oh no. Now we're using it. This sum, right? This is a constant. So this sum is 1. Right? Right? And so now, what's the expected value of this square? It's just the definition of variance. right? And then we say, oh, now we have to put it through the rectifier, right? So the blue goes into the purple. And what does the rectifier do? Well, it's on one side or the other. If it's on one side, it zeroes it. If it's on the other side, it doesn't touch it. So we're going to again assume that it's on a random side. And so the expected value of the square too, because half of them are given. More. Yeah.
So what happens to the number, like, multiple data points actually show this proof of. Because you can't assume that this, like, you can't assume that it's in.
Yeah. Yeah. Well, because all these values are sort of random, and we haven't even looked at the signage yet. This sum, this Z value, half of them are going to, we did a random walk, and half of them are going to end up on the positive side of the negative. The random walk came from the first version of the proof, is that you multiply this by Z. This term over negative. And so when you do the sum, it's like a random walk. And you're going to end up positive or negative. It's zero. Yeah. Okay.
This one, all this thing on.
Yeah.
In that the sum of normal is there. Input coming to right, it's just all the y axis.
All right, so then we get what we wanted, right? Here we get that the expected square was that. So so somewhere did I say we? Here we're doing it. So now you do the sum of the squares and you get one. Yeah. So exactly. There's all, and it proves it's going to give you a certain amount of time, and within that time, you don't have enough change to get out of the wall, and within that time, you get this loop. This is wrong. Yeah, well, I'm not going to give you the punchline. That's all. Wow, that can be talked to if we can get through this bit. All right, so there we go. All right, so now we're going to take some derivatives. All right, so you can see one of the values before it's gone into the and that's one of the outputs, right? And let's take the change in this with respect to this value. And I like to think about it is that the derivative is sort of the weight of the super edge between these. Because it's kind of what is the influence of this value on this value, right? So you could just write, instead of this, you could write this. All right. So what is that? Is if you sum up over all paths from one to the other of the product of the weights in between, right? Assuming the path isn't zero, right? If something along that path hits a rectilinear zero, then it goes to zero, right? So again, we're going to pretend we have enough independence and wave our hands around and everybody gets that. And all right, so then what's the variance of this? Well, if they're independent enough, then the product of the variance is the variance of the product, and you can sum them up. And so, yes, yes. Yeah, this is one super path, and we're trying to calculate it. All right, so right here, the variance of 1 is 2 over n, so the variance goes up by the length of the power of the length of the path, right? Because we're multiplying them, and then each step, right? There's a chance of it being 0, right? So we're gonna kill off a lot of them, right? And then how many paths are there? Right, well, there's an exponential number of paths, and it all adds up to 1 over n. Super path is a path from here to here. We're skipping the length of the path is the number of this path is length 2, right? We go 1, 2. Right? And it has this weight and this weight, so it's this number squared. Right? But how many paths are there? Why is there 2 of them? Because the slides get messy.
Like, roughly how.
Yeah.
And then probably how that.
So here we're trying to jump layer a certain number of layers. Yeah, that's to the power of length. Right, to the power of length. Yeah, I'm not using the length. I mean, it's this could be a non-constant. This could be a big number.
The thing is that the number of paths, the equivalent is 1 minus 2.
Yeah, it's 1 minus because in this case the number of paths is n. Right, because there's a number of fence posts in the middle. Yeah, well, yeah, for sure. This is all right. So you get 1 over n, and this is kind of when I said I had 3 proofs of that things don't grow. This is kind of the 3rd way of proving that things don't grow, because multiple edges, super edges, all act like if it was a single edge. Right. This summation here, it's here the length of the path is 2. So the number of lines in the middle is 2 minus 1. Right. So now we have n choices where to be in here. There's another I have n choices where to be in there.
That's pretty cool to hear. Here you're using no.
Yeah, so we can prove everything all at once. My understanding is that there's many versions of this paper, and previous papers did it for sigmoids, and what have they deal with it? What? This cancels. What are you? Yeah.
It's two, right? You're
Two.
all of them.
Which is the same as our previous proof, and then every layer.
Here we have,
The functions that we're doing rectilinear. Yeah. We're doing rectilinear. It did. It did. At one point, I assumed that we were on one side of the rectilinear. You guys are a hard audience. I do. In fact, my complaint about teaching is that we don't, I didn't say it was a negative thing.
Like raising areas.
Exactly. Well, I do appreciate it. All right. Anyway, there's a super edge acts like this single edge, right? Because things don't grow, right? So it's similar proof is what we did before. All right. All right. So now, yeah, one edge was 3 times. I don't know. I can argue that it's fine. So, right now I was trying to understand it too. All right. So anyway, now we need to take derivatives. Right, so here we got some value of the previous layer, and we put the edges between them, and then right. So this value, right, is just the sum as we always did, right, and then the output here. See, I'm treating this is really a derivative, but I'm treating it as a super edge. So then you can get this sum of these values. Right? If you put it as derivatives, which the blue we had to be the input of the rectifier. That's why it was length versus length from one. And in terms, yeah, let's not get into that. I switched that because I thought the math looked easier, and I might have thrown something under the bus when I did it, but anyway, so you get this double sum, right? And right, so we're looking, and so now what we're going to do is we're going to choose one weight and take the derivative, right? And so you get one of these weights here, and all the terms drop out except the one we're differentiating. Right? So the derivative of this with respect to this weight is the value here. We don't include this weight because that's what we're differentiating with respect to, times this weight, this super weight. Right, you buy that? It's the same. We could be doing it as chain rule, right? The derivative of this with respect to this weight is the derivative of this with respect to the weight times the derivative of this with respect to this, which is this. Same as the chain rule. What? Yeah, well, we did that induction when we talked to this. All right, everybody kind of buy that? And then we're going to do a bunch of things. We're going to take this number and we're going to square it. We're going to sum over all the weights at this level. And we're going to take the expected value. Right? And so that's just plugging in our values. And then here's a miracle step, and I'm not going to read it in paper, but you all will notice. The miracle step is that this sum is only over this, and this sum is only over this. So we can separate the sum, right? Into product of two sums, right? Eric, you good with that? You look puzzled again. What? Oh, no, it's not independent. It's this number, right? I mean, if you multiply these together, right, you get every I, sum over every I and every j of this times this. It's just that the sum is different.
Plus that.
Where? Here? No, because of this product. Right? If you have multiplied two sums together, what do you get? You get the sum of everyone here and the sum, you choose some guy here and some guy here. Right? And then you take this times this. Right? So it gives you this. I did separate out of those. I didn't notice that. So, yeah, and that's going to be true because this value of super weight has to only do with the weights that are over here. And the value of these values only has to do with what's coming here. We're still talking about the good. Everything is possible. Excellent. Excellent. All right. So then this first one, we have the length of this vector is 1. And the second one, we said that this guy is normal with the length over n. So we get the sum is 1. And so this whole thing becomes 1. No, that's just the noise error. If I wrote down 1, Park would complain. Yeah, there's some definition of high probability, and the epsilon is in the high probability. Right. And I must admit that when I do these, one of the things is to be expected.
Where the variance was like 1 over number of parameters. There are d variables. Epsilon is like 1 over d.
So just to tell you what is, I'm just casual about doing induction at the different layers, and the problem with that is that this epsilon grows with the height, and he did that when the length and the depth is big, that's a problem. And so he does a lot more work to prove that this epsilon doesn't grow with the depth. Yes. He proved it for big depths. Yeah. So all of this, there really should be a term in here that has to do with the depth. And he has that a very small dependence on the depth, where if you're naive, it would grow exponentially. Right? All right. So now we're going to put these pieces together a little bit. We have one training data and one R, and this is what our error is, right? So this is my addition, he does a whole page of math that I didn't understand. One line, and this is how I turn it into a vector space for my own sake. All right, he doesn't do the vector space. Yes, for short length of time. All right, so here I'm going to have a vector space with a dimension for every x and for every r. And why are we doing that? Well, then I'm going to have here called loss, where the particular value is lost for those, right? And we can calculate the length of this vector is within, if you ignore the hat, it's exactly the area, right? And then I'm gonna now for every weight in the entire thing, right? So here is L, which layer we are, and then a particular layer you're going to, right? So for each of those, we're going to have a vector, right? And what is that vector going to be? It's going to be the derivative, right? And then we can't compute the length of one of them, but we can compute the length of the sum, right? If you do the length of the sum, it all boils down to the training data times the number of outputs times the levels, right? Because we had this sum here with plus and minus 1, right? Am I losing you? You got anything you want? I mean, here we calculated the sum of these pairs of the derivatives, right? Was plus or minus 1. And so that becomes the length of the vector. And in this vector, just if for this vector, we have a particular vector for particular, each weight here, we're going to have a vector. And that vector is going to have coordinates, which are the derivatives. And so then we sum up the weights of all those vectors, and we get good stuff, right? And okay, so then now we want to take the derivative, right? What's the derivative of the air with respect to a particular weight? Now, Mark's going to complain because this proof is supposed to work for all air functions, and this air function is so perfect for what we're doing. This is just going to be so beautiful. You're going to say, ooh, right? You take the derivative, right? And so you get this loss here times this derivative, right? And that's just the dot product of these vectors, right? So what's the dot product? Well, it's the length with the cosine in between, right? So he never mentioned cosine, of course. He did a lot of ugly math I didn't understand, right? So what could this cosine be? Well, it could be 0 and the cosine, right? The cosine could be, where we got it? Well, you know, it can be 0, or it could be 1, or it could be 0, right? And so all the ugly math that I didn't understand came to prove that we got enough randomness and independent randomness between these two. So the angle is not just somewhere between, and you're going to get some constant. All right. More under the bus. Well, something you can, with high probability, you can bound it above and bound it below. You just need that it's not too small, right? You need high probability it's not 0. I don't care if it goes to 1, right? I just don't want it to be 0, right? Because what my derivatives big, right? All right, so then we square these things and add them up for all edges, as we need to do. And so that squares the length, which is nice because we know the square of the length. We know the square of the length is the air in an M. Right? But sorry, dude, but that's what we wanted. Now you're supposed to say, oh, yes. Right? This constant.
This constant stuff is
Take the cosine. Everything.
the function thing.
If we give a lower bound, it just is 0. Or negative. I didn't even think of negative. Oh, well, we're squaring everything, so I don't think that matters. Yeah, so we go from this line to this line and square things. So I don't care about negative. You worried me for a minute, but we pulled that one out from under the box. All right. Any other questions about this? All right. So this is what we did so far. We looked at random guys, and we're saying we're not making much changes. So the first step is to look at when we change from the random, when we change from random to adding these small weights, then the first thing is to look at how many of your rectilinears split from one side to the other, because that causes a breach. And he proves that not many of them flip. And so those values, he's just going to say worst case things happen to those, because we just don't, because there are not very many of them, right? And then the rest, if you're only over here, over there, then it's linear, right? And so you can really say, here's a linear function. You can say what happens when you move by a little bit. Was that enough of a recover? Because it's all you're going to get from me.
Make the first, the second step depends on how the weight change happens. But if circumventing all of that by integrating vector average and say typical vector is the top element to V now.
Yeah, and let me tell you what happened else here. You're saying we don't know where to go. And it's saying we're going. So we're doing adversarial worst case. Within the ball, the adversary gets to say where you go. Yeah. Well, because weird things happen. It's not, those are non-linear. Oh, yeah. I had a question about this flipping. Let me show you what my daydreaming about the flipping said. Is I was like, suppose we're computing parity. Then if you flip one input bit, then the output changes a lot in a really non-linear way. And I felt that can only be achieved by flipping from one side to the other to non-linear. And so I computed What? Oh, I'm not a speller. Is that spelled wrong? It was, I put that in there to be a joke for you. All right, right. So yeah, you flip, right? Then what happens? And so I did this on this case. I actually did the math. If you have random neurons, same framework, then the fraction of neurons that flip values, just the one input value, 1 over square root of n, the neurons flip from one side to the other. And that gave me confidence that it was computing. And the computing in a nonlinear way.
The error because the ball is much smaller than the pen.
Yeah, the ball's, yeah, exactly. The ball's very small. The ball's 1 over n to some polynomial. The ball's very small.
Sharp point. Yeah, once you're here, you know what I mean, right?
Yeah, yeah. All right, so I am not going to have any claim of proving these because I didn't read this for sure, but it did labels, it did general error function, which is the one that probably because there's an engine. Right, that error function was just so perfect, right? I mean, right, it does other things. It does random stochastic. No, it says you can use any error, so you can do log error, cross entropy, right? It doesn't matter. It says it just doesn't matter, right? Which, right? We're doing fixed, but right, you can have different. Yeah, you can do convolution nets. I had to look up what this meant. It meant that you can skip layers. Oh, by the way, when I read papers now, I grab things that I don't know and put them in ChatGPT. It really helps me. I mean, yeah, it's so much better than Google. All right, so that's that paper. All right, and I just throw these in case somebody asks about them. Hopefully you won't. Those were the actual. All right, so how much do you guys good with time? You have to go. All right. So what's left is what's known that what do I know that's known about generalizing when you to new data. So we can skip that or do that another time or whatever people want to do it now, whatever you want. What? Oh, the one is we want to find a machine fast until we want it to generalize, right? And generally we get it, but what proves in terms of proof, if the weights are really, if we have lots of weights, then we proved it works. And packed learning means a small number of weights, right? So can we get both of these at the same time? And of course, the punchline that you always have to go back to is the proof you can't get both at the same time is if your labels are random, right? Then you can't do better than table lookup. So you need the number of parameters to be bigger than the training data. And there's no way you're going to generalize, right? Because you have no information. Right? What?
Unrealistic distribution. You can't do both of them.
Right. So I was asking people what's known, and what they said me was pretty bad.
So you want to add things.
Yeah, that's certainly the conclusion. Right. Right.
But if path is too strong, you can't expect pattern.
Yeah, so the Reader's Digest, so that's path learning. And then there's VC dimension. And then there's this one problem that path learning requires the number of bits to describe your machine versus the number of real numbers to describe your machine. And so this paper is just it's a disaster because all it tries to do is get around that and it makes things worse. In practice, bits versus real is the problem.
But again, but if you don't take out.
Yeah, exactly. All right, well then yeah, we need to, I need to get more of those yeses so I can add them here. Yeah. And what assumptions are you adding to the function?
The target function is the
Smooth. Right, right. Right.
I learned about the smoothness that.
Well, this paper says if the function's smooth, then you only have to worry about these grid points. But the grid points are still, it's still exponential in the number of, I mean, it's worse than what we were doing. Worse than. And do you get that in practice or in proof? But not in proof. Right, but if you only assume good gradient in the output function, can you prove something? Do you have any other proofs?
No, you just said the first.
So one thing you could say, suppose the output. I actually thought about this, and I know the answer is no. That if all you assume is that the derivative is small of the output, I can still come up with examples where it's random enough that you're not going to be intentional. Yes, yeah. It's just having good slope isn't enough. All right, and so
Slow, but that's why I use the so-called limited time.
what's Lipschitz?
Lipschitz is the one copy chain.
Yeah. Yeah, Lipschitz just a more generous definition of derivative. Any example my mind thinks about derivative is good enough. Well, it's not good enough to. I can give you nice smooth functions whose derivatives are small, and you can't generalize. I'm pretty sure. I mean, I was driving a car when I thought about it, so don't quote me. All right.
They're not working because they are not working now. You join the there's so many parameters. Every single point is possible to change the one parameters. That's why the only thing again is that's the same thing. If you do that type of analysis,
Prove
Kind of done, right?
That
So
there's-
it takes a random, so changing much if you're at a global.
Yeah. No, no, we need to be the right thing. The right thing, so that everybody is on.
There is a distribution where there are many.
I come up with the message, but you got the evil you can happen to these messages to move up, the base by cases, and the move up. You bother, you can, you can, but true, everyone. Plus, you also, speaking the practice, you respond with a very. Nothing changed, just that. This is exactly what. But you come to this. Thus, before come up with something.
And the right place is just having always close to, but not exactly. The right place is always having always just being very small, that's enough.
Lockdowns are very small, those to get.
But not equal to.
Not all you will work. Not equal. You have lots of them. You know, having. This is also about that. Yeah. You don't.
There are too many videos.
Yeah.
The reviews become.
Yeah.
Like first, the number of zero rates are very high. So weight becomes zero. If your group is assuming that half of the inputs activate zero, half of them activate. More bias errors and
Even not on ways, you don't make geography. Yeah. Exactly.
the quantity seems really. So the pulse is respect to just convergence, not everything. What this is open to
And otherwise, that's why I try. When I talk to people. It seems. You use in so many ways. In practice, people do use more weight than number presented. In practice, they overfit.
This is about each
And
other.
when people have been wondering why is overfitting working, when it's, and even when they have more parameters, it's still generalized. So let me just give one last statement here. Like, look at these three, the data is being fit by the green line, right? Which one do you expect to generalize itself, right? This is underfitting, this is overfitting. Right, so this one, what does this one have? It has, the machine has a small slope. Yeah, so here are three statements that I managed to come up with.
This is Please start with the reconstruct the function. This is a suffering series, right? So then as long as the function stays, as long as the function stays, you don't need to do that. Which is a new, you can That's why they reject. You need to put a constraint on the target function.
Yeah, so this says nothing as a target function. This is the derivative of the machine, right? So if you, given the numbers we were looking at, if all you do is you set each weight to be positive, right, then the derivative is exponentially big, right? But the guy returned by our algorithm, and everything was over here is small, right? So this overfitting machine is returning a machine with a small derivative, right?
But second one is also
Yeah. This return by the over-parameterized random. This is the paper we just covered. If you do, I did a little extra math, and it computes that the derivative. Well, we did it already. That the derivatives were small. Yeah, but the overfitting. Which one do you think is going to which one is going to generalize the data you've never seen? Right, so is one in the middle. The algorithm we just covered has lots of parameters. It finds perfect fitting, and the derivatives are small.
So we say nothing about gen. So I guess the context is that none of these papers talk about generalizing at all. Until just before this paper, even convergence was like a pretty big difference.
That's why they global now.
I think the global minima is just like a byproduct of them because people create here they could prove that at any point there is reduced by something.
Well, we want a third picture which is perfect and has a small slope. Right, that's what we want, right? And what they were finding in practice, I think, is if you had small number of parameters, you could get perfect, but the derivatives were big and it wasn't fitting well. And so that's why you started doing things like regularization and keeping your model from not being complex. And that is just trying to keep the derivatives smaller, right? And now people are finding in practice if you put extra parameters at it, it works better. So why does it work better? Well, one explanation is that this algorithm we just covered could give you bad derivatives, but it doesn't, right? And you really do go. Excellent, thank you so much. And then this paper that somebody sent me just saw, which this one I couldn't read the font. And it says that the derivative of our model in the worst case is always at least this, which is a big scary kind of equation. But what does it conclude? That if you want your model to be small, then the number of weights that you have to be much bigger than the number of training data by the dimension of your problem. So this says, well, if you don't overfit, you won't get a low derivative solution, right? And so that makes that it's a justification for having low weights. Not true. I think the bottom line is the function you're trying to learn has small derivatives, and the machine that you can't have small derivatives. Then in the car, I argue that's not enough. But
the other extreme and saying if your data can survive multiple square roots of the number, then it's true. Previously, they were like more reasonable algorithmic models to regularize everything.
the square root.
Right, so why was n much bigger than t? Because you were working with multiple standard deviations, you were working with 1 over square root and you just going that away. And you want that to be like numbers. All of these to still be bigger than t. So this quantitatively swinging the other extreme and saying, oh, we just have a large volume. That's enough. So now I think getting closer to that a bit more. Because somehow there's some cancellation happening in your food. This program people get. So what's that doesn't signalize that?
That doesn't feel like. Oh, good. What I did in the car was take a subset of, you take all inputs, we to the end, finally, you take a subset of them that are far apart from each other. And that's just using a resolving algorithm. Right? And then you put random answers on those points, and you slope them because they're far enough, you can have a small slope in between, right? And you're doing, now you're solving the problem on a problem that's like 2 instead of second and you have a nice small slope, and it's just as bad as the random. That's all it. That's what I did. All right, thanks, guys. And we're ready to meet Friday. Excellent. Take time to Friday. I'm giving this talk tomorrow at 1:30. And we'll see who shows up. But it's only advertising the theory people. It's a theory seminar. Because I don't have the nerve to talk to you. People also, we did an hour and a half here, we had a lot of questions. In the end, we were here for growing. Oh, that was mine. Yeah, that was my making up from what, why did I make it? Who knows? Yeah, yeah. I can try to understand this component. All right.